Hey, Bryce Carlin's here with Robotics Competition News. We're here in 2017 First World Championships in Houston. I'm here in the pit of 971. And I'm with...
I'm Ginger. I'm a team captain on 971.
And so 971 Spartan Robotics, you're out of California. You're very kind of like infamous team for your very advanced...
Thank you.
So you're welcome. I'm always in awe of your control system and the way you do different mechanisms that are just like so like complicated and simple at the same time, just like super well engineered stuff. And this year, I think you've hit kind of like a new high with your intake and shooter mechanism, or your feeder and shooter mechanism, which we call the Serializer.
Yeah.
So I'd love to talk a little bit about the design process that went into that and kind of the iteration and prototyping and how you got to your final fabrication.
Yeah. So, what a question. Our inspiration, we sort of realized we needed to get lots of balls going somewhere really fast. So that was sort of like the initial design constraint. And one of our mentors is really into paintball guns and that kind of stuff. And he actually has one at home, and it has a die rotor, which basically funnels the little paintballs that are inside really, really fast. So that's sort of where we took inspiration, and it basically consists of two counter-rotating things that work to funnel the balls downwards. Ours goes upwards, so we had to change things, obviously. And from there, from the inspiration, we moved to prototyping. So we have a CNC router in our shop, and this year we actually started routing wood, which has been huge because you can blow through wood. It's like vanilla. It's really, really nice to cut. So that's been really amazing. We ran through like 5 full-size iterations of our Serializer with like these massive pieces of wood. We actually blew our prototyping budget by like 500% buying sheets of wood. Yeah.
But it's cheaper than aluminum. So
yeah, and it cuts way faster. It's easy to modify. And so we started with a lot of different things. We initially had these pockets in the Serializer that would sort of push the balls towards the center of the column, but it made it harder for balls to fall into the Serializer. So we took those pockets out and added fins, which were more flexible, plastic fins. And then these fins also worked really well, but we were still having jamming problems. And so another thing we actually tried is having 2 individual rollers that would spin around rather than a hook.
Okay.
So our inside column had one roller going this way and one roller like this on the column. So when it went around, like the ball would sort of go through it like that.
Okay. Yeah.
There's Steve can send you videos and pictures.
Right.
And then that we found worked really well, but it wasn't as fast as the hook. Like we have this hook that really swoops all the balls, and that works really well. So we sort of combined those and had a hook and one of the rollers, because the rollers really helped with jamming issues at that point.
Right.
Because if it were passive, it would be like a problem. Another thing we like to say is like if you have a game piece, you should always be in control of it, sort of like a touch it, own it type of philosophy.
Right.
So like,
really positive control of it.
Yeah, definitely. So like, for things like intakes, shooting mechanisms, and ball feeding mechanisms, as much control as you can have, and like as many degrees of freedom as like the best. As long as it's not too complicated. Sometimes we go too far. And then from there we put the design in CAD. And then once the CAD was completed, we manufactured it again on our CNC router, but this time we used a combination of 3/16 aluminum, 1/8 aluminum, and for the shafts we used a lathe that we have in-house. And then it was assembled by students, and we ran... Serializer, surprisingly, has been one of the strongest mechanisms on our robot. Like, knock on wood. Here, I'm going to knock on wood. Knock on wood, it hasn't broken that terribly yet.
Right.
Our intake and our shooter and our hanger and our gear mechanism have been a lot more problematic. So it's actually been really exciting how well it's worked. A few things we changed. We changed the fin diameter. The biggest problem we have is jamming. So what happens is our Serializer and mostly our intake is very strong. So these wiffle balls crush very easily.
Yeah.
So if we get a crushed ball inside our Serializer, it is not happy, which is actually something our pit crew is working on right now. Let's see what else.
What about electrical power? Because there's all these spinning components.
I got you.
Yeah.
So we found a slip ring that is mounted at the bottom of our center column for all of the wires that need to get down there and are spinning. For the wires that go to our shooter, we have a umbilical cord that sort of goes around. But yeah, the slip ring is what we have.
What's the process of getting that like inspected? Because I know slip rings aren't like super. They're not like really. They're not actually mentioned at all in the handbook.
The slip ring had no mercury in it, and it was also rated for the current, so it was perfectly legal.
Very cool. Very cool. Where'd you actually source that? Because I know like a lot of teams have like tried to like find, or they tried to even like build their own.
Amazon.
Really? Wow. Okay. That's
Yeah.
very cool. And so you found one just like kind of the diameter that you needed, and then just like went from there.
Yeah.
Very cool. So another couple things. The turret and the vision that went into that. I know you're not like too into the software side of it, but the turret, like, and first, well, actually, before we get to software, the machining and the fabrication on the turret and the parts.
Yeah.
You do all that in house?
Yeah. Except for our center column, the rest of the machining was done in-house, either on our lathe or on our CNC router. We have one of our team mentors also has a mill and a lathe at his house, so he helped with a few of the parts, but most of them were done in-house. There's this one large 5-inch diameter aluminum tube that we have for our center column, because we originally had 3 smaller tubes, but we were experiencing a lot of wobble with the shooter.
Okay.
And in order to increase shot accuracy, you wanted to be as stable as possible. So we actually switched to this, I think it's like it's very thick. It might have been half-inch thick.
Half-inch wall?
Half-inch wall.
Wow, that's heavy.
5-inch diameter aluminum for stiffness.
Okay.
And one of our mentors took it into, one of our sponsors has a machine shop, and they have like a live axis tooling lathe, I believe is what it's called.
Okay.
CNC lathe. And he helped us machine that with a bunch of kids. And so that was really cool. And then other than that, we have a epicycloid gear, which is like sort of my child on the robot.
Right.
Basically, what happened is we originally had a bar to ground our turret for the shooter.
And this is for the ring gear that's actually rotating the turret around.
Yeah, this is for the turret. So basically, we originally had a bar to ground the turret, because whenever you have a turret system, you need something somewhere to ground it so that it doesn't just like go crazy.
Yeah. Something structural that it spins on, something that's mounted to the chassis.
Exactly. And so the bar was getting in the way of balls falling into our serializer, and for us, balls were like our game. So we were like, all right, let's take that bar out. And so the solution was to actually have a counter-rotating gearbox that actually opposes the spin of the serializer, and it's attached to the shooter. But this was like a really fast iteration on our turret, so we wanted to be able to machine it in-house, and the laser cutter we normally had access to was down. So we actually used an epicycloid equation, which is like a cycloid equation, which is what you use for rack and pinion gears.
Right.
But it's an epicycloid because it goes around a circle instead of a circle going on a line.
Right.
It's like a circle on a circle. Anyhow, so we used that and modeled a gear profile for 1/8-inch diameter pins. So then we created a pinion out of 1/8-inch diameter pins, and then modeled the gear, the ring gear, and then figured out what reduction we wanted, how many pins we wanted on the pinion, and how many teeth on the ring gear, what would fit best. And then from there we used 1/8-inch Delrin, and we stacked 3 to form the ring gear in the middle, and then the pinion was mostly a lathe part, and then we pushed pins through.
Gotcha. So what I totally lost my train of thought. The Delrin, so the materials that you use.
Yeah.
Have you had any trouble? Because what kind of like RPMs are you going at? Like, is the it's spinning on?
The turret doesn't actually go very fast on that Delrin, because our shooter is just going from left to right, really.
Mm-hmm.
So I couldn't give you an exact number, but if you imagine just like a shooter going from, because it's the way it works is the ring gear is attached to the center column, and the pinion is attached to the shooter. So they're attached to different things, and their only interaction is with their teeth.
Right.
So when you spin the pinion, it'll spin against the ring gear, which is on the bottom, which opposes that.
Oh, okay.
Yeah.
I see now.
So they're like
so the pinion's mounted to the
gear,
to
the shooter. Yeah.
And the Delrin ring gear is spinning with the the serializer.
Yeah, exactly.
Gotcha.
So when the turret goes from left to right, that's pretty much the speed.
Right.
Yeah.
Okay.
It's nothing too crazy. We also actually use Delrin ring gears for our outside. We have an outside cage spins, and our inside also spins opposite of each other.
Gotcha.
They're driven off of a gearbox that's on the side of our robot. We just use 1775 Pro for that, and then use gear reductions. Use gear reductions so we can have opposite spin on the top and the bottom.
Okay.
So
you have one gearbox powering the entire thing?
The spinning part of it, yes.
Gotcha.
So there's a chain that reaches through the bottom of the robot to get to the center column, and then the outside column is driven by a large 420 tooth ring gear.
Okay.
Yeah.
And that's also a machine now, Delrin?
Yeah, that's also Delrin. And we haven't had any problems. Our hood teeth are also out of Delrin.
Okay.
We had a lot of fun with Delrin. We actually did have a problem. Some of the teeth broke at our first regional, but it was like a code problem we went past. I don't quote me on this, but I think we went past a hard stop, so the bottom teeth were broken.
It did like hit the hard stop and then
Yeah, or
kept spinning,
something wrong happened basically, and so we broke a few teeth on the bottom. But those were the teeth that we didn't use anyhow, so we moved our hard stop. It was fine. We replaced it at our next competition.
Very good. Because it's Delrin, it's so cheap and easy to machine. You just like swap it out, has spare parts, super light.
Yeah, it's nice.
Yeah, I think that's probably one of the, as far as like machining goes. So like a lot of teams have like a nice router or a nice laser cutter. They can keep it through robots out of wood. But as far as machining more structural components that are a bit like not wood, Delrin I think is a great place to start that a lot of teams don't use very much.
Yeah, and Lexan. We love plastic. Our entire hopper structure and gear mechanism are pretty much made structurally out of plastic. I personally love making little doodads out of 030. Like if you're ever in a pinch, some 030 Lexan, a pair of scissors is like honestly all you need, because you can bend it by hand, and that flange is actually way stronger than people give it credit for.
Wow.
And so our gear mechanism has actually a lot of 1/8 inch and 030 Lexan on it, and it's just connected with rivets, and it's really strong. So is our hopper for all the balls is also made out of plastic. Plastic is really nice because you can iterate super fast on it. It's cheaper, and it's so much more fun to cut on the router.
It's not, you're not so like crazy stressed out with your huge like expensive aluminum billet. Yeah.
Yeah.
That's very cool.
Yeah, so like we love plastic. I don't know, you're gonna get like shots of that later, but like this entire thing is plastic.
The whole like gear mechanism, hopper kind of stuff.
So like designing with flanges and rivets and stuff like that, you can use plastic in a lot of scenarios. I think actually 1678's 2014 robot, their arms were plastic also.
Yeah,
it was
I remember
crazy.
that.
It was
That
so
was,
cool.
I saw that and I never expected that to work.
The 254 intake this year is also made out of Lexan, like 1/4 inch Lexan.
Right.
Yeah.
Very cool stuff. I think that's about it. As far as control system wise, I know it's something, especially with your. But if you're having, if not, we can talk to someone else about it. If you want.
You can ask, and I will probably not know.
Okay, that's fine. Then we can talk to someone else about it and cut it in.
Yeah.
Is there any other like cool mechanical things you want to talk about in the robot? Cool things you thought, weird problems that you solved, kind of stuff?
Oh, I have a cute one.
Sure.
So we didn't, we don't have a lot of space on our robot. So for our hangar, we needed a ratcheting system along with some. Our hangar. We didn't have a lot of room on our robot, so a hangar was sort of one of those things we had to fit in.
Yeah.
And we decided to drive it off of our intake. So we have two 775 Pros on each side of our intake that drive the rollers.
Okay.
But we also added another sort of reduction for our hangar, so it's driven by those same things. But we didn't want our hangar to be spinning during matches, just in case it catches things and that kind of stuff. So we actually used a one-way bearing on it, so it spins one way but not the other.
Oh.
Yeah, so we actually have a reduction to our hangar. And then when we're intaking balls, it doesn't spin that direction. And when we're out taking balls, it'll actually spin backwards so we can catch the rope for when we're hanging. So it's really nice.
That's very cool. Is that so? That's like kind of what is it like a one-way bearing? Like is it like a ratchet system? Like it's built to a bearing?
Yeah, basically.
That's something that you can source from like McMaster or something?
Yeah,
or?
I think we got ours from McMaster.
Okay, because I've seen a couple teams have like a similar solution that they like manufacture themselves out of like a sprocket that was like ridiculous.
No, one-way bearings were like, that was like cute, like.
That's very, very cool.
Yeah, I like to call clever solutions like cute, when it's like, oh yeah. Yeah,
I think it is.
It's fun.
Yeah, very, very cool. Awesome. Thank you very much.
Yeah, definitely.